Welcome to this webinar titled Faster, Better Organic Chemistry through the use of real-time in situ FTIR technology and software optimized for the organic chemist. Developing a simple and easy-to-use yet powerful reaction analysis system for the organic chemist is a goal that we have had since the introduction of the ReactIR in 1989. While the concept sounds simple enough, it is only through years of experience and generations of evolved technology that this goal can be achieved. Advancements in material science and computing technology is also a contributing factor in making systems easier to use, for example, by allowing us to use fiber optics instead of mirrored conduits for most applications. Finally, we have to acknowledge all the people in the industry and academia who have brought not only visibility to the power of using real-time in situ mid-infrared spectroscopy to studying chemical reactions, but has also shown us how it is best applied. This slide has been used for nearly 20 years to remind the audience about why real-time in situ FTIR is so valuable. It held true 20 years ago and holds true today. There is no substitute for being able to see at a molecular level the changes occurring during a reaction under actual reaction conditions. A review of publications in a peer-reviewed scientific journal illustrates commonly that a true understanding of chemistry can only come about through the use of all the tools available, and that in situ mid-infrared provides invaluable insight alongside NMR and HPLC, among other analytical techniques. While we have talked about the contribution of comprehensive reaction information from ReactIR for many years, it is only today that we have taken a big leap forward by developing not only the instrumentation, but the software design specifically for the organic chemist to make it easy to use kinetic information to solve challenges in organic chemistry faster and with fewer experiments. I am very excited to be able to introduce our latest technology and software, but before I do, it is interesting to be able to take a look back over the last 21 years of ReactIR development history. What started out 21 years ago as a large refrigerator-sized instrument has evolved into what you will see can be tucked neatly away into the corner of a fume hood. Introducing the ReactIR 15. This is the smallest and easiest to use reaction analysis system ever developed. What is immediately obvious is not only its small size, but its simplicity. The footprint is considerably smaller than a sheet of paper. The only utility required is power, as the instrument is sealed and desiccated, eliminating the need for purging by dry gas. Sampling technology is attached via the DS interface, meaning that you simply need to plug it in and it is fully optimized and ready to use. The full range of DS series sampling technologies can be used, which today includes a variety of silver halide-based fiber optic conduit probes, microflow cells, and fiber conduit to sentinel probes, which would typically be used for autoclaves. The fiber conduit probe assemblies have an integrated RTD in the tip of the probe, which captures the temperature of the reaction mass with every spectrum. The temperature trend can then be displayed along with chemical species concentration trends. This not only provides additional valuable information that is stored with the experiment file, but also leaves one more port open on a typically crowded reaction vessel. Status indicator lights on the front panel tell you at a glance that the system is ready to collect high-quality chemical information. I asked my colleague Travis Thompson to take this picture because I wanted to show in contrast the size. The size difference is, in fact, impressive. However, what really stands out to me, yet again, is the simplicity of the ReactIR 15. For the typical chemist, this is a dramatic improvement and makes the ReactIR 15 a system to be used to monitor every reaction. Putting the probe into the reaction vessel is no more difficult than inserting a thermocouple, and with a probe diameter of 6.3 millimeters or a quarter inch, it is actually the size of a typical thermocouple. I have to give credit to Ben Littler from Vertex for the idea of using this type of slide. He showed it at a conference several years ago, and it really had an impact on me. in showing how much progress we have made with software development. Earlier, I talked about the importance of learning from experience. Nowhere is this more important and apparent than with software development over time. In 1995, we released FTIR Software 2.0, which was revolutionary at the time because it was the first software developed specifically for reaction analysis. However, when the software was open, it was a blank screen, so you had to be trained to use the software and could only be very proficient by being a specialist for the FTIR. This is the typical user interface even today for much of what is offered by spectroscopy companies. 5 years later, we released FTIR version 3.0, which you see on the right, which didn't make any significant improvements in usability. It was really the next generation of software, ICIR, that was not just an evolution, but a revolution. The organic chemist is now able to see all the options available in a web browser-like interface. Links to helpful resources are on display on the right, and recent experiments are available with a single click at the bottom. Real-time in situ FTIR data provides a wealth of information about the chemistry. It can tell you how many reactive species are present, how their concentrations change as a function of time, and how their rates change as a function of conversion. It can also provide information about transient and sensitive intermediate species. Many times the information is easy to interpret, and a compound can be monitored simply by trending a peak that corresponds to a functional group change. In some cases, the data is complex and not easily interpreted, which is why software to automate interpretation of the data is critical to success. Concert Live is a software module that is integrated within ICIR software and will deconvolve three-dimensional mid-infrared spectral data, that is, wave number versus intensity versus time, into its individual components. Those components are the reactive species and their rate of change. Concert Live does this in real time without any user input and provides you with mathematically calculated pure component spectra and concentration trends for each of those components. This is especially valuable for gaining information about temperature or air-sensitive compounds and for transient intermediate species that are difficult to get information about using offline analytical methods. IC Quant is our second D2I, or Data to Information module, for ICIR software. Simply put, it makes the task of creating a quantitative method and the subsequent prediction of absolute concentration in real time easy for the non-specialist to implement. The latest addition to our Data to Information software suite is IC Kinetics. Unlike Concert Live and IC Quant, which are integrated into ICIR software as an add-on module, IC Kinetics is a standalone software package. IC Kinetics is a simple graphical method of analyzing how different experimental conditions can influence the speed of a chemical reaction. IC Kinetics seamlessly imports concentration data from in situ spectroscopic measurements from the FTIR or conversion data from reaction calorimetry or heat flow for kinetic analysis, for example, from the EasyMax, the LabMax, or the RC1E. IC Kinetics is based on the methodology called Reaction Progress Kinetic Analysis, or RPKA, which has been pioneered by Professor Donna Blackman, currently at the Scripps Institute. I highly recommend that anybody interested in knowing more about RPKA to read the article by Donna Blackman cited in this slide, which was published in 2005. Donna Blackman also presented a webinar on April 28th where she introduced RPKA and described the basic concepts of RPKA and why it is such a powerful methodology. I would recommend that you watch the webinar, which you can do so on request by visiting the webinars on demand at mt.com/ac-webinars, or by becoming a member of the AutoChem community website, where you can watch webinars on demand anytime you like. So why kinetics? I will reiterate the 3 points that Professor Donna Blackman made in her Why Focus on Kinetics slide during her webinar. The first point is that it improves process safety because understanding how substrate concentrations drive the reaction is key to understanding how to keep the reaction within control. The second point is that it improves process understanding. An understanding of reaction mechanism leads directly to optimizing the synthetic route. The final point on why kinetics is important is that a better understanding of the process from beginning to end leads to process conditions that give consistent results. Much like what we did with FTIR, we should address the value of using IC kinetics. People know why having kinetic data can be valuable, but they are also aware of how many experiments are involved with classic kinetics and how time-consuming classical kinetics analysis is. What IC kinetics does is automates the conversion of kinetics data from IR, heat flow, or calorimetry into easily interpretable, graphically oriented information. As IC kinetics is based on the RPKA methodology, it requires far fewer experiments than classical kinetics does. IC kinetics uses the entire data set from beginning to end, taking into account other influences that occur at high conversions, which reflects real-world synthetically relevant conditions and improves the overall understanding of the process. Finally, RPKA addresses the role of side reactions and catalyst performance, which helps to design processes which are more robust. This example is the acetylation of aniline. I ran these reactions a while ago in order to collect data for kinetics analysis. The procedure complements of Professor John Soa at Seton Hall University in South Orange, New Jersey. I used a single PC with iControl for EasyMax and ICIR for the FTIR control of the instrumentation. Inserted into the EasyMax's vessel is a silver halide fiber conduit probe coupled to a FTIR. Then 50 mils of dichloromethane is added. Stirring was set to 200 RPM for each vessel, and then using just the keypad in front of the EasyMax, I set the temperature of the vessel to 0 degrees, and after the temperature was stabilized, acetic acid was added. Again, the temperature was allowed to stabilize, and then I added aniline in one shot using a syringe. Here is a typical data set shown within the 3D surface viewer of ICIR software. In this case, I have performed an automatic subtraction of the solvent DCM. Therefore, what you see here is just the data that correlates to the peaks for each of the reactive species, so you don't see the solvent at all. So what we can do now is we can actually profile the peaks that correlate to the reactive species of interest to get the concentration trends. In this example, I use concentrations of 100 millimolar for both the anhydride and the aniline. So knowing the starting concentrations of the aniline, we now have the information we need to perform the kinetics analysis using IC kinetics. I can then import these trends directly into IC kinetics just by using the icon at the top right. You can see that it says, the second one in from the right, it's import data from ICIR. And I can add the region of the trend that I want to analyze simply by clicking on the new data set icon and then graphically adjusting the left and right borders of the region. In this case, I have adjusted it to cover the region of conversion from about 20 to 80%. I have two curves here because I have two different data sets, one from each different excess experiment, which is the way we run the experiments within the RPKA methodology. So the rate equation is calculated, and it tells me that it's approximately first order with respect to aniline, and it's fractional order with respect to acetic anhydride. This is just an illustration really about how to use the software, so I'm not going to go into a lot of detail. We're going to cover that in a later webinar, and I have not verified these results yet. The real value of the software is where we go from here, and I'll use a different example to illustrate this point. The example I'll use is an aldol addition reaction. I can illustrate that by using the simulate function. We can start mapping out the design space so that you can achieve product quality by design without having to run a lot of experiments. So in this example, we have 3 different curves because we have run 3 different excess experiments. The rate equation tells us that this reaction is approximately first order in compound 4 and approximately half order in compound 5. And for those that want more information about the meaning of fractional orders, again, please reference the work by Donna Blackman I mentioned earlier. So when I click on the Simulate tab, I can quickly see for a range of experimental conditions on a 3D map showing conversion as a function of time based on any set of initial conditions. In this case, my parameters are the initial concentrations of my substrates, which I can change. And here I've input a range from 0.1 to 1.0. So the range should, at a minimum, cover the synthetically relevant range, and ideally should go outside that range a little bit. So after doing that, by clicking on the map, the conversion over the desired range is displayed as a function of time. And that's what we see in the 2D graphs. So I have input that it should calculate the time to 95% conversion. So at the bottom of the conversion graph, you can see the text tells us that the calculation tells me that based on the initial concentrations that I've chosen, the time to 95% conversion is 81.2 minutes. Now, with this information, you can go back to the lab and run several more experiments to verify that the kinetics behave as predicted. In this way, you can eliminate unnecessary experimentation time and costs and quickly find the optimal process conditions based on this set of experimental conditions. I hope that you have all found this webinar useful. I'm just listing here a few additional resources where you can learn more about the products and solutions that METTLER Toledo offers for capturing accurate real-time data that can be used in the kinetics analysis by IC Kinetics.